Welcome back to the deep dive. Today, we're diving into something, well, fundamental. Light itself. We use it constantly, obviously, but the actual mechanics behind it, whether it's, a light bulb or a super precise laser beam, it's all happening down at the subatomic level. We just sort of take it for granted, don't we? But how does that energy actually become light? What's the process?
Well, we've gathered quite a stack of scientific sources on this, looking at light emission, energy levels, different kinds of light sources. Our goal here is really to give you the inside track on the physics that makes everything from stars to your phone screen light up.
Okay, let's get into it then. We want to understand how matter turns energy into photons, all governed by quantum mechanics.
Exactly. And the core idea, the sort of big picture view, it's actually surprisingly straightforward. All light, doesn't matter where it comes from, is made when electrons jump between specific discrete energy levels within an atom. Those shells you might remember. That's the quantum condition, and it really dictates everything about the light we end up seeing.
All right, so let's zoom in on that atomic engine. The sources call this first step excitation. So talk us through this quantum jump.
Okay. So you've got an electron just sitting comfortably in its lowest energy level. Its ground state, we call it. To get it to move, you need to give it some energy. Could be heat, could be electricity running through, maybe even just bumping into another particle. If it absorbs just the right amount of energy, bam, it jumps instantly to a higher energy level, a higher shell.
So the atom's holding on to this extra energy for a moment, but it's not stable up there.
Not at all. That excited state, it's incredibly temporary. The electron, wants to get back to stability, so it immediately looks to fall back down to a lower, more stable level, and that's where light comes from. As it drops down, that extra energy it absorbed has to go somewhere. It releases it as a little packet of light energy, a photon.
Wow, okay, so that quick drop is the birth of light. So say an electron drops from energy level 3 down to level 1. How does the atom decide what color photon to spit out?
This is where the quantum rule's just so neat. The energy of that photon, let's call it $E, is directly tied to its frequency, phi number. Our sources all point to the Planck relationship, EW, E's, OT's, HV, where H is just Planck's constant, a fixed number. So because the energy difference between level 3 and level 1 is always exactly the same for, say, a hydrogen atom, the energy of the photon it releases is also fixed, absolutely set.
Right, so the color isn't random at all. It's like a receipt for how big the energy drop was. A big drop means a high-energy photon, high frequency, maybe blue light or even UV. And a smaller drop gives you a lower energy, lower frequency photon, like red light.
Precisely. The atom isn't guessing. It's releasing the exact amount of energy needed to bridge that specific gap between levels. And that energy value directly determines the frequency, which to our eyes is the color we see.
Okay, this idea of precision, specific jumps giving specific frequencies, it makes me think light must carry some kind of unique ID. Which brings us nicely to section 2, light's fingerprint. If energy levels are fixed for each element, then each element must emit its own unique signature of light, right?
You're spot on. That's exactly what happens. If you take a light from a hot gas like sodium vapor or maybe neon, and you shine it through a prism, you don't get a smooth rainbow like you might expect. Instead, you see what's called a line spectrum. The light only shows up at very specific frequencies, specific colors. It looks like distinct, bright colored lines with dark gaps in between.
Huh. So those yellowish streetlights you sometimes see, that's sodium vapor. And the atoms are only making photons with the energy that corresponds to yellow light.
Exactly right. That pattern of lines, the line spectrum, it's like a unique chemical fingerprint for every single element. If you analyze the light and see that specific pattern of lines, you know without a doubt which element produced it. It's unmistakable.
Okay, so that's the precise light from excited gas atoms. But what about the more, common glow you get from just heating things up, like an old-fashioned light bulb filament? That's called incandescence. Why does simple heat produce a full rainbow, a continuous spectrum, instead of just those specific lines?
That's the key difference. Incandescence is what happens when you heat a solid material really, really hot, thousands of degrees Celsius, for a tungsten filament. The atoms in that solid aren't just having neat individual electrons jump between specific levels. The whole structure is vibrating incredibly intensely because of all that heat energy.
Because they're all just shaking violently and bumping into each other, radiating energy kind of randomly.
Pretty much, yeah.
Yeah.
Because they're packed together and vibrating like crazy, interacting constantly with their neighbors, the electron energy transitions aren't restricted to those few specific jumps. Instead, the material emits energy across a whole broad range of frequencies, continuous spectrum. You get all the colors blended together, the full rainbow. And the key thing here is temperature. The hotter the object gets, the brighter it glows overall. And the peak of the light it emits shifts towards higher frequencies. That's why things go from red hot to orange hot to white hot, and eventually, if you could get it hot enough without melting, towards blue.
Okay, that makes sense. Now, building on that fingerprint idea, if atoms emit only specific colors when they're hot, what happens if you take cool atoms of that same element and shine a continuous rainbow through them?
Great question. That leads us to the absorption spectrum. It's essentially the reverse process. Those cool gas atoms will actually absorb photons from the continuous light source, but only photons that have the exact same characteristic frequencies that the atom would normally emit if it were hot. So when you look at the rainbow that comes out the other side of the gas, you see dark lines right where those specific colors, those specific frequencies have been snatched out, absorbed by the atoms.
Whoa, so the element acts like a filter, removing its own signature colors from the light passing through.
Precisely. And this isn't just a lab trick, it's hugely important. Astronomers noticed dark lines in the spectrum of sunlight way back in the 19th century. Those Fraunhofer lines, as they're called, were the absorption lines from elements in the cooler outer layers of the sun's atmosphere. By matching those dark lines to the known emission spectra of elements here on Earth, scientists could figure out what the sun is made of, without ever going there. That's actually how helium was discovered. They saw lines in the sun spectrum that didn't match any known element on Earth, so they figured it was a new element. Named it helium, after Helios, the Greek sun god. It's an amazing cosmic chemical ID system.
Incredible. Okay, let's shift gears slightly. Sometimes things glow, but it's not just direct emission. There's fluorescence. We see this with like UV lights making posters glow brightly. What's happening there?
Right. Fluorescence is a bit different. It's usually triggered by high-energy light, often ultraviolet or maybe deep violet light, hitting a material. This high-energy photon kicks an electron way up to a high-energy level, just like before. But instead of dropping all the way back down in one go, releasing another high-energy photon, the electron takes a series of smaller steps back down.
Ah, so it absorbs one big packet of energy but releases it as several smaller packets.
Exactly. It absorbs one high-frequency photon, like invisible UV, and then quickly emits multiple lower-frequency photons, which are often in the visible range, green, yellow, orange, whatever the material is designed for. The key defining feature of fluorescence is that it happens fast. The glow starts almost instantly when the UV light hits it, and it stops almost instantly when you turn the UV light off.
Okay, so that's fluorescence. Quick conversion. What about phosphorescence then? That's the stuff that genuinely glows in the dark, right? Like long after the lights are out. How is that different?
The core difference is timing, persistence. Phosphorescent materials have something special in their structure. Think of them as little traps or intermediate energy states. When an electron gets excited in these materials, it can fall into one of these traps where it's actually sort of stable or metastable for a while.
So it gets stuck partway down, like hitting the quantum snooze button instead of going straight back home?
That's a perfect analogy. It hits snooze. It's trapped in that intermediate state, not immediately falling all the way back to the ground state. Because it's temporarily stuck, the emission of the light photon is delayed. The electrons slowly leak out of these traps over time, seconds, minutes, sometimes even hours later. That slow leakage of energy as light is what makes things glow in the dark. That persistence long after the initial energy source is gone is what fundamentally separates phosphorescence from fluorescence.
Got it. Okay, let's connect all this amazing atomic physics to the lights we actually use every day. Section 4. Modern light technology. The old incandescent bulb, the kind with the hot wire. Our sources really hammer home how inefficient that was.
Oh, absolutely. They're terrible from an efficiency standpoint. You put electrical energy in, but only about 10% of that energy actually comes out as visible light, the other 90%. Just listed as infrared radiation heat, basically. That's why those bulbs get so hot.
Which is why we moved on to things like fluorescent tubes. They use a smarter atomic trick, right, involving gas excitation.
Yes, much cleverer. Instead of relying on brute force heating, fluorescent lamps use an electric current flowing through mercury vapor inside the tube. This current excites the mercury atoms, making their electrons jump up and fall back down, just like we discussed. But here's the trick. Mercury atoms primarily emit high-energy invisible ultraviolet UV light when they do this. That UV light then hits a special white powder coating on the inside surface of the glass tube. That powder is a phosphor material.
Ah, so the phosphor coating fluoresces. It absorbs the invisible UV and re-emits it as visible light.
Exactly. The phosphor coating performs that quick energy conversion we talked about, absorbs UV, emits visible white light, much more efficient than incandescence because you're not just generating tons of waste heat.
Okay, fluorescent was a big step up. But now, the real efficiency king seems to be the LED, the light-emitting diode. What's the quantum mechanism there? It's not a gas, it's solid, isn't it?
That's right, LEDs operate based on semiconductor physics. It's a solid-state device. Instead of exciting electrons in individual gas atoms, LEDs work when electrons cross a very specific energy gap within the semiconductor material itself. It's called the p-n junction. You push electrons across this junction using electricity.
So the electron still makes a jump, an energy drop, but it's happening within the structure of the solid material.
Correct. There's an energy band gap in the semiconductor. When an electron falls across this gap from a higher energy band, the conduction band, to a lower one, the valence band, it releases the energy difference as a photon. And just like with atomic energy levels, the size of that band gap dictates the energy, and therefore the color, of the photon. Engineers can design semiconductor materials like gallium nitride or aluminum gallium indium phosphide with very specific band gaps to produce specific colors, red, green, blue, and so on, very efficiently with very little heat loss.
Which brings us to maybe the most engineered, most precise form of light we have, the laser. We know lasers are directional, they're monochromatic, just one pure color, one frequency. But the sources emphasize this other property, coherence. What does that actually mean, and why is it so important?
Coherence is really the defining magic of laser light. Monochromatic means all the photons have the same frequency, the same energy, but coherence means they're also perfectly in phase. Imagine ocean waves all hitting the beach at exactly the same moment, perfectly synchronized. Laser light waves are like that. All the crests line up, all the troughs line up. This perfect synchronization is what makes the beam so incredibly intense, focused, and capable of traveling long distances without spreading out much.
Okay, same frequency and marching in perfect lockstep. How on earth do you force atoms to cooperate like that?
It relies on a process called stimulated emission. It's quite clever. First, you need to pump energy into the laser material, which could be a crystal, a gas, a semiconductor, to get a whole bunch of its atoms into an excited, unstable energy state. More atoms excited than not. That's called a population inversion. Then you just need one photon of the exact right energy to come along and interact with one of those already excited atoms. When that incoming photon stimulates the excited atom, it doesn't just cause the atom to drop down and emit a photon, it causes it to emit a photon that is an exact identical twin of the incoming one. Same frequency, same direction, and crucially, same phase.
Wow. So one photon goes in and two identical, perfectly synchronized photons come out.
Precisely. It's a cloning process for photons. And now you have two photons that can go on and stimulate two more excited atoms, producing four identical photons, then 8, 16, and so on. It's a chain reaction, an amplification of perfectly coherent light. That's what builds up the intense, focused, coherent laser beam. And that coherence is why lasers are so useful for everything from reading data on a Blu-ray disc to performing delicate surgery or cutting through steel.
What an amazing tour. We literally went from the tiniest quantum leap inside one atom, that fundamental EFF idea, and followed the thread all the way through. We saw how it leads to the continuous rainbow of hot objects versus the sharp, unique fingerprints of light from specific elements and gases.
And the common theme, right through fluorescence, phosphorescence, LEDs, lasers, it all comes back to electrons moving between those specific energy states. Sometimes it's heat making them jump, sometimes electricity, sometimes even light itself, like in stimulated emission. But that core quantum process is behind all the light we see and use.
Right. So here's something to think about, building on all this. We figured out what stars are made of using those simple dark absorption lines, the Fraunhofer lines, just by understanding basic emission and absorption. That was world-changing. Now we have lasers light we've engineered to have this incredible coherence, purity, and precision. What new cosmic secrets, maybe subtle things that depend on interacting with exactly the right kind of light, might we be able to unlock or measure out there in the universe using this ultra-precise laser technology?
That's a fascinating question. The possibilities are certainly exciting. We'll definitely have to keep exploring. We'll catch you on the next deep dive.